This is lesson 9.1b. In this lesson, we're going to continue to talk about radicals, and we're specifically going to talk a little bit at the beginning here about rationalizing the denominator. So when a radical is in the denominator, so remember in the bottom of your fraction, you can multiply the fraction by an appropriate form of 1 to eliminate the radical from the denominator. So think similar to when you made similar fractions, right? If I had 1/2 and I was trying to make it into eighths, let's say, I would have to multiply the top and bottom of my fraction by 4, because 4 over 4 is 1. It doesn't change the quantity of the fraction, it just changes what it looks like, okay? So we're going to be doing something similar to that, but we're going to be using radical expressions to help us do that. So let's take a look at example 1a. So letter A, we have the square root of 5 over the square root of 3n. So we are trying to simplify this so that we no longer have a radical in the denominator of our fraction. So in order to do that, I need to multiply by a form of 1. So I'm going to multiply. If I want the radical to go away, remember that I would have to essentially square it, so multiply it by itself. So I'm going to multiply the top and bottom of this fraction by the square root of 3n. So that means we have, under the radical for this one, 5 times 3n is 15n, still the square root. And then we have 3 times 3, which is 9, n times n, which is n squared. And again, we've got our radical. So then if I'm going to simplify this, the top is the square root of 15n, while the bottom is square root of 9 is 3, square root of n squared is n. So the square root of 15n over 3n is our final answer. For letter B, we have 2 over the cubed root of 9. So when I'm thinking about this one, remember I am attempting to get rid of the radical, right? So if I simply did the cubed root of 9 times the cubed root of 9, that's not necessarily going to undo that radical that I'm looking for, right? Because this one is a cubed root. But if I think about my perfect cubes, right? I think to myself, well, 27 is a perfect cube, right? 3 times 3 times 3 is 27. So if I want to undo that radical, I know that I could multiply 9 times 3, but I have to keep it a cube, right? So I have to multiply by the cubed root of 3, because like over here, we had 5 times 3, we got our 15. If I do the cubed root of 3 times the cubed root of 9, then I'll have the cubed root of 27. So I'm really looking for that perfect square to put under my cubed root, or sorry, perfect cube to put under the cubed root. So I'm going to multiply the top and bottom of this one by the cubed root of 3. I guess we can make this a color so we can identify that we are multiplying by something different than we started with. There we go. So 2 times the cubed root of 3 is just 2 times the cubed root of 3. Over 9 times 3, like we talked about, is 27. So the cubed root of 27. Now the top can't simplify. It's still just 2 times the cubed root of 3. But on the bottom, the cubed root of 27 is 3. So that will be our final answer. 2 times the cubed root of 3 over 3. Now for example 2, we're going to be talking about conjugates. So a conjugate, let's make sure we can see that. There we go. The conjugate is, we have the binomials a times the square root of b plus c times the square root of b, and the second binomial a times the square root of b minus c times the square root of d. So in these two binomials, a, b, and c are rational numbers, where rational means that we can make it into a fraction. You can use conjugates to simplify radical expressions that contain a sum or difference involving square roots in the denominator. So it's not just a plain old square root like we had in the previous question. We have an actual subtraction question here. So in order to simplify this, we are still going to be multiplying by a form of 1, but we're going to take this whole denominator, and we're, instead of using subtraction, we're going to be using addition. So it's kind of like, think about using the opposites like we did when we were solving equations. So what I'm going to do is I'm going to, let's move that up a little bit more, multiply the top and bottom of this question by 2 plus the square root of 3 over 2 plus the square root of 3. Because notice in the top, those two binomials, one of them was positive and one of them was negative. We started with the negative, so we're going to multiply top and bottom by the positive version. So when we multiply these two things, we're going to be multiplying the term 7 by both the 2 and the square root of 3. So 7 times 2 is going to give us 14. And 7 times the square root of 3 is going to give us plus the square root of 3. So it's essentially like multiplying like the distributive property. Then on the bottom, we've got 2 times 2, which is 2 squared. And then negative square root of 3 times the positive square root of 3. So that's minus the square root of 3 squared, right? Because I've got 2 square roots of 3, so I'm taking that and squaring it. So then we're going to simplify this a little bit more. Nothing on the top. Oops, I forgot my 7 in here. 7 times the square root of 3. I wrote the arrow and never put the 7 in there. There we go. 7 times the square root of 3. So nothing on the top here can be simplified. So we've got 14 plus 7 times the square root of 3 over 2 squared is going to give us 4 minus the square root of 3 squared. Remember, squares undo square roots. So the square root of 3 squared is going to give us 3. Top's still the same. 14 plus 7 times the square root of 3. 4 minus 3 is 1. So if we want to write this in the most simplified version, of course, if I divide anything by 1, it remains the same. So 14 plus 7 times the square root of 3 would be our final answer for that one. So we have this complicated fraction at the beginning here with our radical in the bottom. Once we simplify, we no longer have a fraction, and we could just simplify from there. All right, continuing on with solving using like radicals. Like radicals are radicals with the same index and radicand. You can add and subtract like radicals in the same way you combine like terms by using the distributive property. So let's take a look at this example, because I think that's going to be the easiest way for us to understand what we're doing here. So we have example 3, and we're going to do letter A first. So we have 5 times the square root of 7 plus the square root of 11 minus 8 times the square root of 7. So what I like to do sometimes is kind of rearrange this to put the things that are similar together. So like when we used to rearrange our equations, put all the x's together, all the y's together. So we're going to do that here. Notice I have two terms that have a square root of 7 in them. So I'm going to rewrite those together. So I have 5 times the square root of 7 minus 8 times the square root of 7. And then I didn't use this plus the square root of 11 yet. So again, bring it down. So all we did from this root to this root, just rearranged it. I put the things that match together and then everything else just got rewritten. All right, so now in order to combine, think about my square root of 7 as being like my x variable in past questions that we've done. So the square root of 7 is what makes them the like terms. So I'm going to take what is in front of those, and I have a 5 here and I have an 8 here. So I'm going to take that, since we're multiplying both of these numbers times that square root of 7, I'm going to put them into parentheses, and I'm going to take my 5. Notice that this 8 has a subtraction sign in front, so it's minus 8. That whole thing times the square root of 7. Still haven't used the square root of 11, so we're going to bring that down. 5 minus 8 is negative 3. So we have negative 3 times the square root of 7 plus the square root of 11 that we never did use at that point. Or up to that point, I should say. That's our final answer, because we're just simplifying, right? We don't know what this whole thing is equal to, so I can't get it down to, oh, I know this, that. They just want it simplified. If they asked you to do it without the radicals, then I could go farther, but they didn't ask us to. That just said simplify it in radical form. All right, so letter B, we have 10 times the square root of 5 plus the square root of 20. So right now when I'm looking at this, I'm like, well, I don't really have any like terms, right? I don't have either one of them with a matching radical, radicand under that radical, anything like that. But I am starting to think to myself, well, I do know that 20 is 4 times 5. And I have a square root of 5 right here. So I'm wondering if I could find a way to get it so that I have, excuse me, some like terms here. So I'm going to rewrite my 10 times the square root of 5 because I haven't done anything with that. But I'm going to rewrite this 20 as the square root of 4 times 5. Now in doing this, I just realized, hey, look, 4 is a perfect square. So if I'm taking the square root of 4, I know that that's going to give me 2. So right now I've got 10 times the square root of 5 plus the square root of 4 is 2. So 2 times the square root of 5. So I can't get a perfect square with 5, so I'm just going to leave it as square root of 5. But for 4, a square root of 4 gives me that 2. Now I have some like terms, right? They have that matching radical. So I have 2 plus 10, or sorry, 10 plus 2 rather. 10 came first. It's addition, it doesn't really matter, but we'll stick in the same order. Times the square root of 5. 10 plus 2 is 12. So 12 times the square root of 5 is our final answer for this one. It's most simplified in radical form. All right, let's do letter C. So letter C, we have the square root of 5 times the quantity, square root of 3, minus the square root of 75. So first thing we have here is we've got some distributive property, right? So just like when we would have a regular whole number or integer and we would multiply it by the terms inside the parentheses, we're going to do that again. So square root of 5 times the square root of 3, and the square root of 5 times negative square root of 75. So square root of 5 times the square root of 3, we're just going to rewrite them as square root of 5 times the square root of 3, minus the square root of 5 times the square root of 75. So we have 5 times 3 is 15, so we've got the square root of 15 minus 5 times 75 is 375, so we've got the square root of 375. Right now when I'm looking at it, I'm like, okay, well, I don't really have any like terms, so I'm trying to figure out, well, what could I split up a little bit? So I realize, and again, if you don't know this right off the top of your head, I would always start by checking what's under here, especially if that's the only other radical I have. I would start by checking that, see if I can divide it evenly, and then I could make some like terms with that. So I would start with that. So if I did 375 divided by 15, I get 25. So I have the square root of 15 minus the square root of 25 times 15. Hey, look at that. 25 gives us a perfect square, right? Let's give ourselves a little bit of color here. So this 25 times 15. 25 was our perfect square. So we have square root of 15 minus the square root of 25 gives us 5. Square root of 25 is 5 times the square root of 15. Now remember, even though there's no number here, that invisible math that we have sometimes, right? We have a whole number of 1 outside this. So we have in parentheses 1 minus 5 times that square root of 15. 1 minus 5 gives us negative 4. So our final for this one is going to be negative 4 times the square root of 15. So that's our simplified radical form. This is lesson 6.3a. In lesson 6.3a, we're going to be talking about exponential functions. An exponential function is a nonlinear function, and it is in the format of y equals a b to the x power. A is not 0, it's not equal to 0. B is not equal to 1, and b is also greater than 0. So we can't have b as something that's smaller than 0. As the independent variable x changes by a constant amount, the dependent variable is multiplied by a constant factor, which means that the consecutive y values form equivalent ratios. So the ones that come right after another will create equivalent ratios. Remember that ratios are fractions. So let's look at example 1. Does each table represent a linear or an exponential function? So if we're looking at A, if it's linear, remember it goes up at a constant rate. We are adding the same amount to each side, and the ratios will reduce to be the same fraction. So as I look at the y value, this y is going up by 2. This one's going up by 2. This one's going up by 2. The x values, looks like from 0 to 1, we're adding 1. From 1 to 2, we're adding 1. And from 2 to 3, we're adding 1. So if we were to make these into ratios, we would do rise over run or 2 over 1. This is A. So we have 2 over 1 for all 3 of those. And since all of them are 2 over 1, right? We've got 2 over 1, 2 over 1, 2 over 1. Those would all reduce to equal 2. So they're all the same. 2 divided by 1 is 2. So this goes up at a constant rate. We're adding to each y value the same amount as x is adding the same amount, which means that this is a linear function. For part B, as we're looking at it, our y value from 4 to 8. When we first look at it, sometimes we think about, what am I adding? Well, I'm adding 4. As I go from 8 to 16, no, I would be adding 8. And then I would be adding 16. So adding isn't giving me a constant rate at this point. So I know it's not linear. I do, if I'm looking at it, 4 times 2 equals 8. 8 times 2 equals 16. 16 times 2 equals 32. So this is times 2. We'll use the x to show times in this one. And the x value is also going up at the same rate. So while the y is getting multiplied by 2, the x value is being added by 1. So as the x value increases by 1, the y value increases by times 2. And since we're multiplying by 2, let's take a look back at our variable, or our definition of exponential functions here. We're looking at a times b to the x power. We have to make sure that we're looking at this last sentence. As the independent variable x changes by constant amount, so x is changing by 1, that the dependent variable y is multiplied by a constant factor. So looking, y times 2 gives us the next one, times 2 gives us the next one, times 2 gives us the next one. So because as x is increasing by a constant rate, y is increasing by the same factor, that times 2, then we know that this one is an exponential function. One way to try to remember this is that the difference, looking at linear versus exponential, notice linear, we're adding something at a constant rate here on the y's, and on the y for exponential, we're multiplying at a constant rate. For example 2, we're going to evaluate these functions for the given value of x. So for example, letter A, so example 2a, we have negative 2 times 5 to the x power, and we are plugging in 3 for x, so this x right here is going to be replaced with 3. So we have negative 2 times 5 to the third power. Remember, order of operations tells us we have to do our exponents before our multiplication. So 5 to the third power is 125. That answer times negative 2. Oops, I forgot to put the y equals here. That tells us that y equals negative 250. For part B, we have y equals negative 3 times 1/4 to the x power. And again, this time we're going to replace x with, 1/2 for that one. So I have y equals negative 3 times 1/4 to the 1/2 power. Now, if we think about our previous knowledge of exponents, remember that when we have something to the 1/2 power, it's the same thing as taking the square root of that number. So if we think about it, we've really got y equals negative 3 times the square root of 1/4. Well, the square root of 1/4 is 1/2, because 1/2 times 1/2 equals 1/4. Negative 3 times 1/2. Let's make this negative 3 over 1. So negative 3 times 1 is negative 3. 1 times 2 is 2. So we have y equals negative 3 over 2. So if we had to the 1/3 power, remember we could have taken the cube root of the fraction inside and then multiplied by negative 3. So you just have to remember those rules we talked about with our exponents. That will make things a little bit easier for you on these. This is lesson 6.3b. In lesson 6.3b, we're going to continue talking about exponential functions and graphs. And in this section, we're looking at something called an asymptote. And what that means is as we make these graphs, notice how they continue, but they're going out here and this one never touches that x-axis. This one over here also never touches the x-axis. The graph up here, if you'll notice, this is where a is greater than 0, and we had b that was greater than 0. Down here is when a was less than 0, when b is greater than 1. I meant to say 1 up there. Over here, we have the same idea, but this time b is greater than 0 but less than 1. So thinking about when we have a fraction, so b is a fraction. If a is greater than 0, you're going to have your graph up here. And if a is less than 0, you're going to have your graph down here. But notice neither one ever cross over that x-axis. They come super, super close to it, but they never actually cross it. Because if you think about this, if b is a fraction, let's say we're using a fraction 1/2, and we're consistently cutting something in half, in half, in half, in half, in half, we never actually get to 0. We just keep chopping smaller and smaller and smaller sections, but we don't actually get down to 0. And that's the idea here, where we're never going to cross over x because I can't cut that thing down to become less than 0 if I'm just cutting it in half or by that same amount every single time. So we're going to take a look at example 1. And in example 1, we are going to be graphing 2 different functions. And once we do, we're going to compare them to their parent function or their original function. And then we're going to talk about the y-intercepts and asymptotes of the graph, as well as the domain and the range. So as we're looking at it, the first thing we want to do in order to be able to graph is we need to make a table of points. So for example 1a, we're going to choose some x values, and I like to choose some positives and some negatives. So I'm going to choose negative 2, negative 1, 0, 1, and 2. And in order to get the y values for these x's, I have to plug them into our equation that we're given. So for this, f of x equals 4 times 2 to the x power. In this case, we're going to have to the negative 2 power. And remember, when we have a negative exponent, we flip the fraction. So this was 2 over 1, now it becomes 1 over 2. And then we raise it to the power of positive 2. So 1/2 to the power of 2 is 1/4, because 1/2 times 1/2 is 1/4. 1/4 times 4 is 1 whole. So next to this negative 2, plugged in for x, we got 1 whole. If I plug in negative 1 right here, so I flip it, so it's 1/2. 1/2 to the first power is 1/2. 1/2 times 4 is 2. 2 to the 0 power is 1. 1 times 4 is 4. 2 to the first power is 2. 2 times 4 is 8. 2 to the positive 2 power is 4. 2 times 2. 4 times 4 is 16. So now I have 5 points that I can plot on my graph here. I'm going to count my x-axis by ones. So every other line I'll count by ones. And my y-axis, I'm going to count by twos. All right, so we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And down here, -4, -8, -12, -16, and -20. So every line is worth 2 going this direction. I just only labeled every other line. So I'm going to plot these, and I have -2, 1. So -2 and 1, since it's counted by 2s, we're going halfway between. And then -1, 2. So -1, 2 is right down here on this line. 0, 4, right here. 1, 8, and 2, 16. So we're going to be connecting the dots. And notice that it kind of curves down and around towards here, but never actually will cross. So as I'm looking at this, my y-intercept is 4. Because remember, where x is 0, that's the y-intercept. We'll label it y-int. Let's compare this to its parent function. So if we look at the parent function is basically the function minus this 4 in front, because that's 4 times the original 2 to the x power. So if I look at that, then I have the red one is our parent function. So this is the original. And the blue line is the one that we just graphed on our paper. So notice that the blue line is steeper than the red line is. But notice they both come very, very, very close. And if we were to zoom in, you would see they never actually touch this x-axis. They just get super, super close to it. So the asymptote for example number 1, letter A, is the x-axis. So it gets as close as it possibly can, but never touches it. So the asymptote for this one is the x-axis. Now let's talk about the domain and the range. So remember from previous lessons that the domain is talking about all those x values, and the x values for this one, if you look at it, I could continue to plug in x values to infinity, both directions. And I can plug in any of the numbers left to right that I want to, and I would be able to figure out the value of y. So because of that, because I can plug in any value that I want, and it would still work, right? Because I'm approaching this, I can plug in the x and it's going to go this way. I can plug in the y, it's going to continue to go up this way, or the x over the side, it goes up this way. So I'm plugging any value I want. That means that the domain for this is all real numbers. I'm going to abbreviate numbers with just that hashtag symbol for numbers. And for our range, the range, again, is our y values. Notice that the entire graph right now is above the x-axis. All the values that we've gotten for y so far have been positive. If I continue this line up to infinity, I have all these positive y values as I keep going up. As I come down this way, because of the curve, because our asymptote is the x-axis, it's never going to touch the x-axis. It's never going to cross the x-axis. Therefore, our range is all of those numbers, but they have to be greater than 0 because none of them went below this x-axis. So none of my y values can be below 0. So when we put this in as our answer, we would say that it is y, so all those y values that are greater than 0. All right, let's take a look at example 1b. Again, we're going to draw ourselves a table. We're going to fill in values. So I'll use -2, -1, 0, 1, and 2 again. And when you make your own table of values, you can select the numbers for x that will work best for that equation. So sometimes these are the most appropriate. Sometimes, depending on what's in the equation, we would have other numbers that would work better. So taking a look here, this time we have f of x equals -1/2 to the power of x. Now remember, this is the same idea as saying -1 times the answer of 1/2 to the x power. So I'm going to, when I rewrite it, I'm going to plug in or remind myself that this is the same as -1. And then I have 1/2, and I'm going to use this -2 power first. So just like before, with our exponent rules, that negative in the exponent means I flip my fraction, so now it becomes 2 over 1 to the power of +2. Answer times -1. And then 2 to the power of 2 is 4. So -1 times 4. -1 times 4 gives me -4. So my first value here is -4. If I plugged in -1, again, I flip the fraction, so it's 2 over 1. 2 to the power of 1 is 2. 2 times -1 is -2. 1/2 to the power of 0 is 1. 1 times -1 is -1. 1/2 to the power of +1 is 1/2. 1/2 times -1 is -1/2. 1/2 to the power of +2 is 1/2 times 1/2, which is 1/4. 1/4 times -1 is -1/4. So now on this graph, when I label my x and y axis, I am still going to use, actually, I think I'm going to do every other line on this one. So I'll count each line as a half. So this will be 1, 2, 3, 4, -1, -2, -3, -4, 1, 2, 3, 4, -1, -2, -3, and -4. Okay, so I have the point -2, -4. So -2, -4. So we're down here. We've got -1, -2, 0, -1, 1, -1/2. So each of these lines was a half. So here we go right there. And then 2, -1/4. So that's right there halfway between 0 and -1/2. So we're going to, I like to turn mine this way when I connect the dots. So when we look at our graph, if we are trying to look for the asymptote for this one, it again looks like it is approaching the x-axis. So if we're approaching the x-axis and never touching it, the asymptote is the x-axis. Now I want to show you the parent function for this graph like we did for the last one. So notice that the red line again is our parent function. If on the top here, and our function we just graphed on our paper is this blue one. So it really looks like we reflected the parent function across the x-axis. And like we were just mentioning, if we get zoomed in on this, we'll notice that it's getting really close, but it's not actually touching that x-axis. It just gets very, very, very close to it every time. So now that we are looking at that, we need to discover our domain. So the domain for this, if we look at it, again, I could plug in any x value I wanted to. It's showing up on both sides of that y-axis. So I could plug in any x value that I want. It's going to continue to go down this way. It's going to continue to go over this way. So my domain or my x values would be all real numbers again. And our range, when we look at it this time, all of our values are below that x-axis. So they're going to get very close to it, but they're never passing into that positive range. So for this, the range would be all numbers less than 0. Now for example 2, we're going to be looking at this graph y equals 4 times 2x to the 2 to the x minus 3 plus 2. And we're looking at it and trying to graph. Now what I want you to notice is this is almost the exact same graph, or equation rather, that we have up here. They're very similar. The only difference is we subtracted 3 from our exponent and then we added 2 to the overall equation. So in this one, our parent function is this one that we graphed in example 1a. And one of the things that we can notice is if we graph both of these together, you'll notice that the x values are slid to the right and the y value is slid up. So if I graph both of these side by side on the same graph, we will see both of those things. So our parent function is again the red one. Here it is. That's what we graphed earlier. And here's our blue one. And if we're comparing these points, what you're going to notice is it's sliding to the right and it's sliding up. And what we have is the points 0. Actually, let's start with our negative 2, 1. According to what is here, we know, based on the rules of these exponential functions, we know that if we are changing our exponent here, they have the general format of it is y equals a b to the x minus h plus k. Now, because the original format is minus h, we are going to, anytime you are using h, that means that you're translating horizontally. So h will translate or slide it horizontally. So if I have minus h, or whatever that number is, it says minus 3, minus 5, then I'm going to be moving my graph to the right from its original. And if it says plus h, I'm going to be moving it to the left. Because this is like negative 1 times h, so normally we would think right is positive. Well, it's saying the opposite of that positive or of that negative direction. So the opposite makes it move to the right. And if we have minus k, this one we're going to be doing what we normally do, we move down because the original one is positive. And if I have plus k, I'm going to be moving up. So if I picked one of the points off of my original parent function, I picked negative 2, 1, and if I'm moving it according to this, I'm moving to the right because of the minus. I'm moving right 3. So 3 spaces to the right from negative 2 becomes positive 1. And 2 spaces up, 1 plus that 2 would be 3. So I have a new point of 1, 3 on my graph. There we go. And if I was at 0, 4, 3 spaces right would be 3. And 2 spaces up would be 6. So I have the point 3, 6. So 1, 2, 3. 1, 2, 3, 4, 5, 6. And then if I chose 1, 8, then this would become 1 plus 3 is 4. And 8 plus 2 would be 10. So I'd be at 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you connect to make your line. This is lesson 6.4a. Lesson 6.4a, we're going to be talking about exponential growth and decay. If we look at our sheet here, it talks about exponential growth. And exponential growth occurs when a quantity increases by the same factor over equal intervals. Increases is exponential growth. Okay. So if we're looking at this formula here, this is how we would write our exponential growth. And we have a factor of b, and that is the sum of 1 and the rate of growth. So whenever we're talking about exponential growth, we have 1 plus r. So 1 plus that rate. And a is your initial value or that starting amount. And you can't really see it very well, but here are parentheses around r1 plus r. And it's raised to the x power to give us our y. So y equals a times the quantity 1 plus r raised to the x power. And this is the formula that you're going to use anytime you're talking about exponential growth. So sometimes they'll give you the values for the different parts, and you'll have to use them to find missing values. So if we look at example 1, the inaugural attendance of an annual music festival is 150,000. The attendance y increases by 8% each year. So right here it talks about increasing, so we know that we're talking about exponential growth. And the rate by which it increases is 8%. So it says write an exponential growth function that represents the attendance after t years. So we're going to take this formula that we had, and we're going to apply it to the information that we were given in the example. So for part A, we have, let's just write down our original information. So a times the quantity of 1 plus r, since we're talking about exponential growth, to the x power. So I'm looking at it, it says that I'm starting, the initial attendance is 150,000. So if it's our initial or our starting value, then we are going to plug that in for a in our equation. So 150,000. We know that the 1 is always there. And then we're going to add the rate. So if I'm looking at this, our rate, r, is the percentage. So percentage rate or percent rate. but I have to write it as a decimal. So remember, when we're talking about percentages, percents are always out of 100. So if I'm talking about 8%, I'm going to do 8 divided by 100 to get the decimal version. So this becomes 0.08. So that's what's going to go in here. Okay, and then we have to raise it to the x power, and x is the amount of time that has elapsed. So they're telling us in part A that the attendance after t years. So instead of writing x, this time we're going to write t. And once we figure this information out, or if we knew what t was, then so the value that we're looking for in this instance, the amount of people, is that y that we have here. So anytime we want to write an exponential equation, we do want to simplify wherever possible. So the only thing we can simplify really in this one is within the parentheses, and we could rewrite it as y equals 150,000 times 1 plus 0.08 is 1.08 to the power of t. So this is our equation that we're using for part A. Part B says, how many people will attend the festival in the 5th year? So what we have to think about for this is we have to think about the amount of years. And when we're talking about the different years and things, the t equals 0 is the first year that they did this festival. So if t equals 0 is the first year, then the 5th season that they're doing this, we would do 0, 1, 2, 3, 4. So the 5th season is the t would be 4. So we have y equals 150,000 times 1.08 to the 4th power, because that initial year is year 0. So if we were to do 1.08 to the 4th power and then multiply by 150,000, we're going to get 204,073.344. But we're talking about people, and we can't have 0.344 people, so we're going to round to the nearest whole person. So this would be y is about 204,073 people in that 5th year. All right, so for example 2, before we get to that part, we're going to be talking about exponential decay as well. And decay occurs when the quantity decreases, so decay is decreasing. And it's the same general idea that we had in our exponential growth formula. So it does start y equals, sometimes it might start f of x equals. We have that original amount a, but this time in our parentheses, we have 1 minus r. And 1 represents like 100% of something. And in exponential growth, we're adding the rate because we have to keep 100% of what we had plus the additional percentage. And in decay, we have 100% of what we started with, and we're taking away by a certain rate every time. And then again, it's to the x power. So we're going to look at these two tables down here in example 2, and we need to decide if it is exponential growth, exponential decay, or if it's neither one of these things. So as I look at it, I'm going from 0 to 1, I'm increasing plus 1. 1 to 2 is plus 1. 1 to 3 is, or 2 to 3 is plus 1. Down at the bottom, from 270 to 90, in order to get there, some people might say, well, if I divide by 3, when we're talking about exponential functions, we're always talking about multiplying. So dividing by 3 is the same thing as multiplying by 1/3. And the same thing goes here. If I multiply by 1/3 from 90 to 30, and multiply 30 by 1/3, I'm going to get 10. So when I look at this, I'm multiplying by a factor that is less than 1. So if I multiply by something less than 1, but greater than 0, then I know that I am dealing with an exponential decay situation. So my rate is greater than 1, but less, or sorry, greater than 0, my goodness, but less than 1. This is r for rate. Now we're going to look at our next table. On the top, we are increasing again plus 1 each time. Now on the bottom here, from 5 to 10, I'm multiplying by 2. From 10 to 20, I'm multiplying by 2. From 20 to 40, I'm multiplying by 2. So this is a rate that is greater than 1, greater than 0 actually. No, greater than 1. So because it's greater than 1, we have an exponential growth circumstance. So our rate is greater than 1.